be volcanoes. We'll get to that shortly. I'm Art Lerner-Lam, and I am co-chair of the 75th Anniversary Committee. This is our 75th anniversary, and we're celebrating throughout the academic year. Having been founded in 1949 with Doc Ewing, and now working to talk about the science of the future and the science that we're doing today. Uh, we are just a few logistics before we hop in. Um, the format here will be a series of short lightning talks, 5 or 10 minutes, and then we'll have open discussion and questions. Please hold your questions until the end, but put your questions into the chat or raise your hand. We'll be monitoring both the chat box and the participant box for raised hands. And I'll call on you to ask your question verbally. Uh, so just take yourself off mute and do that. We do appreciate it, by the way, if you keep your camera on so that we can see who we're talking to. I see in the list already a bunch of returning friends and new faces as well. So welcome to you. Welcome to you all. Today's speakers will be Ally Peccia, who's a graduate student in the Department of Earth and Environmental Sciences and at Lamont. She'll be followed by Einat Lev, who is a Lamont research professor and a lecturer in the Sustainability Science program, in addition to doing quite a bit of work. And we'll turn to both of them to Einat shortly. But I think we're going to be starting off with Ally. So, Ally, the screen, I should say, is yours.
Awesome. All right. I guess presentation check. Does that look good to everybody? Great. All right. I'll just jump right in then. Yeah, thank you so much for introducing me, Art. And I'm really excited to be here to celebrate the 75th anniversary of Lamont and talk about volcanoes. Yeah, so my research focuses on big explosive volcanic eruptions. And the question that we're really interested in answering is, what will be the impact of the next major volcanic eruption? And it's important to know that not all volcanic eruptions are created equal. And so how big do I mean when I say big? Well, volcanologists use a scale called the Volcanic Explosivity Index, which is imperfect, of course, but useful. It's similar to the Richter scale of rating earthquakes in that it's logarithmic. So it goes from 0 to 8, and each step in the VEI scale is an eruption of magnitude 10 times greater than the last. I'll note also that mass eruption rate for modern eruptions that we can observe is kind of a better indication of the explosivity of eruptions. But when we're thinking about past eruptions, VEI is a useful oversimplification. So at VEI 0, we have our non-explosive style of eruptions. So this is what we think about with Kilauea, as well as the recent eruptions in Iceland. In the interest of time, I'll jump straight to VEI 4 eruptions, which are much more explosive, often producing pyroclastic flows and ash falls. The eruption of Mount Pelee, Martinique in 1902 is one of the deadliest eruptions in recorded history and had nearly 30,000 fatalities. Jumping to VEI 5, these are, kind of the canonical explosive eruptions that we think about, like the eruption of Mount Vesuvius in 79 AD, as well as the eruption of Mount St. Helens in 1980, producing up to a cubic kilometer of ash. All the way up to VEI 7 eruptions. These are quite colossal, even more colossal than VEI 5 and 6 eruptions, and can have major global effects. For example, the eruption of Mount Tambora in 1815 created global climate cooling that actually inspired Mary Shelley to write Frankenstein, because she had to be inside during her vacation to Switzerland in the very dreary weather. And so, sort of charted this new course of horror with Frankenstein. VEI 8 eruptions are, of course, our supervolcano Yellowstone style eruption that would have a massive impact on the shape of our world. I'm really interested in VEI 6 to 7 magnitude eruptions because they have a low but not unreasonable possibility of occurring, and they would have major consequences potentially globally. However, we haven't observed many VI 6 to 7 eruptions. The last century or so has been a time of relative volcanic quiescence for the size of eruptions. And so we have to study eruptions of the past in order to understand the kind of impacts that this eruption might have. So our toolkit for looking at past eruptions is varied, which is incredibly useful. We can think about tree rings and other paleoclimate indicators, giving us a sense of the toll that these eruptions might have on the climate. Ice cores give us a sense as to the timing and the magnitude, as well as potentially preserving ash that was deposited following these eruptions. My favorite, the rock record, can tell us about the style of volcanism as well as the amount of gas released with the help of handy-dandy melt inclusions, which record the original composition of the magma, included the pre-erupted gas content. And these are sort of a happy accident of nature. These little blobs of silicate melt are about the width of a human hair, and still can provide really phenomenal insights into the pre-erupted gas content of magmas. And climate models and historical records also offer insights into, the predicted impact of volcanic eruptions as well as the human impact that we see. So I'll jump straight to our case study. I'll talk about the eruption of Okmok-2, which happened in 43 BCE. So Okmok is a volcano along the Aleutian Arc, so way out here in the middle of the Pacific. And its caldera-forming eruption in 43 BCE generated 50 kilometers of pyroclastic flows and left this, really massive 10-kilometer wide caldera in its wake. And recently, the tephra from this eruption were recovered from the Greenland ice core. And when they analyzed the geochemical composition of that ash, they saw that it matched the eruptive products from Okmok-2. Now, if there's any historians or historical enthusiasts in the audience, you might think about 43 BCE as being sort of an interesting time in the world. Julius Caesar was assassinated in 44 BCE, which led to a period of political instability in the Roman Republic and Ptolemaic kingdoms. And in looking into the historical record, we can see that numerous historical sources report cold weather and widespread famine in the Roman Republic due to agricultural failure. And in fact, Plutarch, when recounting the life of Julius Caesar, notes that the brightness of the sun was darkened. Similarly, in Egypt, there was famine recorded in multiple historical sources, as well as a record that the Nile did not flood for 2 years in 43 and 42 BCE. And Cleopatra actually declined to provide aid to Cassius and what was left of, the Roman Republic on the grounds that Egypt was racked by famine during this period. And so volcanic eruptions can have a major impact on the surface because of the gases that they release during their eruption. Sulfur in particular is one of these climate affecting gases. And when injected into the stratosphere, it can form sulfate aerosols that reflect incoming radiation and cool the Earth's surface. You might, remember that quote from Plutarch where the brightness of the sun was darkened. And so we were really interested for Okmok in thinking about how much sulfur was erupted. And using our handy-dandy melt inclusions, we could measure the pre-erupted sulfur concentration and scale that up to the total amount of mass erupted and estimate that about 62 teragrams of sulfur were released in this eruption. For some context, that's approximately 3 times the sulfur emissions from volcanoes globally every year in just one eruption. To further investigate the climate impact of this eruption, we looked at some paleoclimate records and ran, with the help of our NASA GISS colleagues, some climate models to simulate cooling at 3 different stratospheric sulfur loads. So our most extreme case being that all of that sulfur was injected, and then some lesser cases beyond that. And what we find is that in order to generate the amount of cooling that we observe from Northern European tree rings and in Chinese cave deposits and speleothems, that there must have been about 16 to 21 teragrams of sulfur injected, which is really important when we think about the climate sensitivity of these big injections of sulfur in forward looking if this type of eruption were to happen in the future. And, in the spirit of celebrating Lamont and its legacy, I also really want to point out how important the work that we do at Lamont is to generating these kind of results. And, I think the key to that is that we have research that spans a variety of disciplines from the tree ring lab, which really is a leader in paleoclimate reconstructions, as well as volcanologists like Einat and I, who study the erupted rocks, as well as the gases that come out and monitor these volcanoes. And also, the atmospheric science community, which runs climate models and different simulations to think about how these eruptions might impact our modern world. Yeah, and those kind of interdisciplinary collaborations are really key in answering the question, what will be the impact of the next major volcanic eruption? So with that, I'll turn it back over to Art and Einat.
Oh, thank you, Ally. I hope all of you find it as boggling to me, to yourselves as it is to me, that without Earth processes, we wouldn't have Frankenstein in our society. We'll talk about that later, Ally. Let's get back to that. But lots of good historical connections there. All right, and your turn.
Hey, let's see how that goes. Can you see my screen or my presenter view?
Presenter view.
Is that better?
Yes.
There we go.
Excellent. It's always a 50-50. Hi, everybody. I'm Einat Lev. I'm a Lamont research professor, and I study volcanoes. And I wanted to talk to you a little bit today about, after we heard how devastating volcanic eruptions can be, what can we do about it? So here's just an updated map of the volcanoes that are currently erupting or have erupted or been in unrest in the last 3 months, that you can find if you go to the Smithsonian Institute volcano program. So there's a lot of them. So everybody asked me, oh, did you hear about that eruption? And like, yeah, which one? There's always between 15 to 40 volcanoes around the world that are actively erupting. So that's just something to keep in mind. So we have to keep an eye on them. Here's one reason why, because a lot of the global flight paths go over active volcanoes, and the ones in red, the regions in red show where there's volcanoes that are likely to produce ash that would intercept those flight paths. So these would be the Aleutians and the kind of the ring of fire that I'm sure you're all familiar with. So definitely something we want to keep an eye on. If you've been following the volcanology news, you might have heard that Mount Spur, right next to Anchorage in Alaska, has been showing a lot of signs of unrest, a lot of seismic activity and gas coming up, and is now at high alert. If that one erupts, it's a big problem for air traffic and the residents of these cities. So unlike earthquakes, sometimes volcanoes do provide us some signs that they might be getting restless and might be ready to erupt. So what we need to do is look at them, record the data, do it in real time so that we're ready and not, 1,000 years later, come back and say, this is going to happen. So I want to tell you today about major
talks about volcanoes, what's being done.
Please mute.
One of these signs that have been recognized over the past decade is a change in the chemical composition of gases, or the ratio between carbon and sulfur gases that come out of a volcano. This is work in Costa Rica that showed that when that ratio spiked up, there was eruption following, and then again a few years later. This is work by our collaborators, Tobias Fischer and Martin de Moor. So there's, skip forward. Besides gases, there's lots of different other signs that we can look at. Seismic activity, ground deformation, gas flux, gas composition, topographic change, thermal emissions, magnetic and electrical signals, infrasound, many different signs and different types. So what we need to do is really a multi-sensor integrated array. And this is a picture from the National Academy of Science report about what we should do to study volcanoes. So we felt the calling to do that. And with Terry Plank and myself leading a project at Lamont that's called AVERT, or Anticipating Volcanic Eruptions in Real Time, that's been fully funded by the Gordon and Betty Moore Foundation. The goals are to provide novel instrumentation and array development that would provide real-time open data to improve eruption forecasting. And it's very much based on academic and observatory partnership. And the partnerships, the beginning was with the Alaska Volcano Observatory, and then has expanded since to also work with Costa Rica's OFSICOI and Universidad Nacional. And we're now cultivating a partnership with Cerna Geomin in Chile. Our target volcanoes have been Okmok, which you've already heard about, and Cleveland, a neighboring volcano, a little over 100 kilometers or 80 miles away from Okmok, but completely different behavior. And Poás in Costa Rica, and coming up will be Villarrica in Chile. At Okmok, AVERT was able to expand the deformation network and install multiple new instruments like soil temperature probes, CO2 probes, magnetometers, and really expand the network of sensors on the island. For example, this new station that we put here is really important for detecting the ongoing deformation off the island. So it keeps inflating like a big balloon. And at some point, it would erupt like it did last at 2008. At Cleveland, nearby, there was really not much before AVERT came. And then we expanded by adding 3 new stations that each of them has multiple instruments. All these colored dots show the different types of instruments. So like you said, remember, we said multi-sensor arrays are key for detecting all of these different signs that volcanoes give us. Here's a picture of our super site. It has so much going for it. The geophysics site, with a GPS and a seismometer and magnetometer. And then we have a gas camera scanning doors, have a visible and an infrared cameras and a weather station. And it's all being telemetered in real time through radio to a hub that has a satellite link. Really key part of our network is the edge computing capabilities. We have these single board computers that control the systems that let us optimize telemetry and power, and also allow new instruments to get plugged in later. This was a first continuous telemetry of DOAS data or gas flux data from the elutions that was enabled by this super site. Since then, we've detected interesting things like deep seismicity or seismic swarm under Cleveland. And then there's new instruments that haven't really been used before, like a magnetometer that looks at the change in the magnetic field under the volcano, and soil probes that look at CO2 and temperature over time. We also started developing innovative technology with the imagery that we have, for example, automatic classification of the quality of images. So you can see based on the time of day that we only get really high visibility, high quality pictures, say if you want, of the plume on a fraction of all the images being collected. So to optimize telemetry, which is something everybody at any observatory and remote site would want to do, this kind of algorithms are important. AVERT philosophy is that everything is going to be open source, the products as well as the software. So we're selling, sharing our plans and our codes with the community. But you may have noticed we wanted to look at eruptions, and neither Okmok or Cleveland have erupted. So this Alaskan bear has kind of gone to sleep, and with things, ideas of Hunga Tunga in mind. So what we said is that, okay, let's find something that may be a little bit more active. So we went to Poás in Costa Rica, which is this amazing volcano that's really just about an hour drive from the capital. So really important for hazards as well. And look what it did. It did erupt. This is an explosion in the summit collected by our IR camera just a few days ago. And it's been doing these kind of explosions repeatedly over the last few months. The AVERT network for us included adding a multi-sensor site at the Mirador, or a viewpoint for tourists that 20,000 tourists visit a month, and then also 2 at the rim, as well as 2 further fields to help detect deformation and seismic events. And you see all these like multi-sensors talk is now coming into play when we are able to look at acoustics of explosions together with the soil CO2, again, a novel instrument, and earthquakes. So it's all really pushing the envelope on what can be detected. Another push that we did was to install the first stalling telemetry on a volcano, and that expand how we can monitor volcanoes around the world where there's no cell phone network or no line of sight for radio. We got very different types of images here at POAS, so we were able to do this kind of automatic classification again, as well as do an image segmentation to look at the size of the lake, which has been shown to be correlated with explosions. We were able to run community workshops with people from many different universities and countries, and just invited people to try new things, like this low-cost gravimeter that haven't been tried in the field before, or capturing aerosol and microbes, and a semi-portable mass spectrometer that has never been taken to the field before. In our last workshop that we did just last month, there was a lot of drone activity. The team from University of Alaska landed a drone with a soil probe for CO2, a collection chamber that collected soil gases. This team from University Nacional flew a bottle to sample the lake water. And a team from University of New Mexico flew a drone with a Gegenbach bottle that opened the vacuum right at the plume and collected some noble gases. The Lamont team flew a visible and thermal camera drone. You can see the circulation in the lake and the plume here and here. And with the changes in the lake level, this really highlights the changes in where the center of degassings and circulation happen. With this, with the Lamont drone, we're able to produce orthomosaics, as well as digital elevation models that help us track changes in the structure of the crater, as well as highlight the hot areas, not only in the 2 lakes, the 2 main vents, but also the fumaroles where gases come out at the wall of the crater, like here. And these are really important because there's a lot of cracks and deterioration of the rocks there. And these have been sites of collapses of the walls into the lake and triggering eruptions. We also got new connections with local collaborators like the power company that gave us instrumentation to do magnetic survey all around the rim. This is Connor, a postdoc, carrying that equipment, as well as the gravity survey. So I hope I get you kind of a run of all these really new things that we're doing with the AVERT project and all these different sites, and it's gonna keep going. So thank you.
Thanks, Anat. Thank you. You and Ally both are using a remarkable assembly of different data types to talk about volcanoes in general and their eruptions specifically, but from very different perspectives. But let me turn to Ally first, actually. Ally, you're a graduate student. And, the typical life of a graduate student is nose to the grindstone on, if you will, a very narrow set of data or laboratory work. How do you engage as a graduate student with all the different disciplines that are required to fulfill your research objectives?
Yeah. I think that's a really good point, and again, highlights one of the reasons that it's really great to be a graduate student at Lamont. Because I think although we are very focused on our specific discipline, I spend a lot of time in the lab looking at melt inclusions under a microscope. If I sit down at lunch one day next to an atmospheric scientist and he or she asks me about my research, I have to be able to explain it in a way that is accessible. And that's sort of exactly what happened with this OCMOC collaboration. We had lunch with an atmospheric scientist, Lorenzo Polvani, at the Lamont Cafe, where all great collaborations are forged. And he got really excited about, our research and said, "Hey, actually, that is really interesting to me, and I think we could work together." So I think it's been really fulfilling and definitely challenging to push yourself to think about how the work you do is relevant to other people. But I think it is also what really pushes the science forward, right, and keeps us on the cutting edge of problems that are very relevant to, people in earth science at large, but also the questions that are relevant to society. Because it's great for me if I know how much sulfur came from this volcano, but that's not, I think that most people don't care so much about that unless it might have an impact on them.
Okay, we'll return to that in just a bit, but let me turn to Anat as well. Anat, when you came to Lamont, you were known as as I say, a computational fluid mechanicist, fluid mechanic. You were working on convection, basically, Earth convection, and now all of a sudden you're, a leading volcanologist in terms of your observational work as well as your theoretical work. So, what was that transition like?
Yeah, that's accurate. My PhD was looking at numerical simulations of mantle convection and subduction processes. But towards the end of my degree, I felt like I wanted to have a bit more of a direct impact on hazard preparedness and people's lives. And I thought, okay, I have a skill set. I can run models, develop models, look at observations. Where can I apply? And ran into the volcanology crowd, and there's just so much that needed to be done in terms of modeling, in terms of model benchmarking, testing, developing. And my entry point was lava flows. So I study the dynamics of lava flows and magma properties. So that was kind of a sort of an easy transition in terms of the math and the models, but opened up a lot of opportunities for actually seeing what I was modeling, which was lacking for me in my PhD. And now I have tremendous opportunities to go and see how the lava is actually moving. So is my model right or wrong?
Yeah, both of you are working, if you will, on eruption events. Okay, in the case, Ally, you're looking at events with a significant explosivity index, what people in the insurance world talk about high impact, low probability events. And similarly, and not, you're talking about events that have very high impact when they occur, but they don't occur frequently. So, how do you actually approach that problem? This is an interesting problem in earthquake analysis as well. The most damaging stuff happens infrequently, and so we have to, if you will, try to extrapolate from common occurrences or actually understand these high impact, low probability events as a separate class. So let me start with you, Ellie. Are these sorts of events a separate class from what normally happens? I mean, can you take some of the tools you have looked at in your paleo work and apply them to more frequent events?
Yeah, that's an interesting question. Yeah, so I guess what I'll say in terms of a different class is that yes, these events, aren't something that we should wake up and be worried about every single day necessarily. But when we look at the frequency of past eruptions, they are events that happen, as far as we can tell, once or twice every 1,000 years or so. And so I think it's about identifying what vulnerabilities we have to those events and trying to come up with some level of preparation. Um, yeah, I guess in terms of thinking about can we apply some of these things to smaller events, I think certainly thinking about the gas that comes out of volcanoes is definitely something that can have local effects in addition to global effects. So even Poas volcano, which Einat talked about, emits tons of sulfur all the time. And although that sulfur doesn't necessarily make it to the stratosphere to have a global climate effect, it does come out in acid rain and affects the nearby communities. And can even, just by being in close proximity to the volcano, have effects on, people's health. So that's, definitely something to consider for smaller, more frequent eruptions. And the tools that we use to study those are similar. So for POAS, for example, we've also done some melt-inclusion work on that volcano as well to think about what is the sulfur content of the magma itself.
In that, when you instrument a volcano, I mean, one of the fascinating things here, particularly with the AVERT project, is how many different signals you're actually looking at. And presumably that's giving you some sort of fingerprint for the volcano as well. Are you seeing from one volcano to another some similarities, or is every volcano unique?
Um, yeah, that is a popular question because you like to infer from one volcano to the other, especially if you have one that is monitored and one that is not, and all of a sudden seems to be waking up. But some research that has been done towards finding analog volcanoes or sibling volcanoes has not been very conclusive. You can try, but honestly, some volcanoes are not even repeating their own behavior. So that has been a challenge. You think about Kilauea, oh, it's always going to ooze out these quiet lava flows. Sure, it's a problem if they turn out to erupt in the middle of town, but it's still going to be the Kilauea thing. But then Kilauea itself had big explosions in the past. So it's sometimes it's a little hard to know, even between neighboring volcanoes like Okmok and Cleveland that are presumably on the same conditions, but one has big inflation events that ultimately have big explosions. Cleveland just trickles out the gas all the time. So yeah, it's still open if we could do that.
So the ultimate solution, if you will, might be something like avert everything everywhere all at once. In some
Yep.
you get same thing for earthquakes, by the way, as well. Let me remind everybody to put your questions into the chat or raise your hands. We'll turn to that shortly. But if any of you have ever, I suppose a number of you have been to Italy around Naples and so on, you see Vesuvius looming over what had happened in 79 AD. Ally, have you been to Naples or have you visited?
I have actually, yeah, I visited Pompeii.
What are some of your observations resulting from that trip?
Yeah, I think I think it really is quite scary. If anybody's ever been to Pompeii, they could probably say the same. And even thinking about the eruption of Mount Pelée on Martinique, is sort of similarly frightening in terms of the speed at which these pyroclastic flows move, um, and just sort of the devastation that they can have locally. So I think visiting Pompeii is certainly a harrowing experience, especially when you see sort of the richness of the culture. Like even when I visited, I remember touring through the bathhouses, and you see some of the stalls where people would be serving foods up, and it's really easy to sort of imagine the people being in this town at the moment the volcano erupted. And if you go to the Met, you can actually see a villa that was recovered from the ruins of Pompeii, with sort of like a gnarled iron window frame in it. So I definitely, in order to, get a sense of, how quickly civilization, even close by a volcano, can be affected by these eruptions, I would encourage people to do that.
There's sort of an irony that's illustrated around Vesuvius, and that volcanic soil tends to be very fertile. So it's populated quite a bit, by people trying to grow things, especially important around Vesuvius and others. All right, let's turn to the chat as well. And I see Jeff Greenspan has been active there. So Jeff, is your microphone working? Do you want to
I don't know. Can you hear me?
Yep.
Can
we
you?
can. Good.
Well, I'll just start with the first question that I had then, which is how rapidly can a magma storehouse be reestablished in a volcano after an eruption? Over.
Well, all right, Einat, why don't you try that one?
I think it depends on the region that we're talking about, whether it's plume supplied ocean island or a subduction zone, but it's it varies a lot. Can be hundreds of years, like we just saw in the Reykjanes Peninsula, until there was enough magma accumulated to start a new round of eruption. So it can be every few decades, depending on the volcano.
Is there any way of determining that by the instrumentation that you have, the size of the chamber, as it were?
The ground deformation tells us the change in pressure and the depth at which it's occurring. So there's always a trade-off between size and volume change. In that sense, seismicity can help us constrain the depth. So we can see if there's kind of a lot of activity, maybe there's a lot of supply as well. And then there's techniques like Ally that can help us after the rocks come out to tell us what.
Can an eruption actually change the location of a magma chamber after the eruption? The location of the magma chamber might change, leading to an eruption at a different site on the same volcano. Over.
So the thinking right now is that it's not so much a magma chamber like a balloon with a straw, like you used to think about that. It's more of a mush or magma supply zone. So there's pockets of different levels of melt content, all through the crust under the volcanic system. And then depending on the size of the volcanic eruption, some may get triggered and combine and some may not. So in that sense, there's always kind of a redistribution of the storage during an eruption and before and after.
Thank you.
Bit like the plumbing in my own house. I spring a leak in one spot, fix it, and then I get a leak in another spot.
Right.
Ken, you've got your hand up.
Yeah, my question's for Ally. I'm a geochemist, so I've been fascinated in that the geochemistry community for argon radiometric dating tested that, and they came very close to demonstrating that the argon really works, because that's only 2,000 years in the past. So that's a level of my interest. Question about the sites there in Pompeii. About how many houses have they sort of preserved to, find the shells of the people that were killed? And are they still doing excavations of that, or is it kind of completed and that area is covered over?
Yeah, that's an interesting question. I'll say that I'm not an expert on Pompeii, just a visitor. But
yeah, I'm asking as a visitor, of course.
Yeah, right. So I think I'm not sure an exact number of houses, but I know that they were excavating another part of the city. And that's actually where the villa and the Met comes from. It's not directly in the city of Pompeii that's already been excavated, but I think it's on the northern side that is still under excavation. And at this point is potentially open to visit. So I'd love to hear from you if you go, what your experience is.
Well, it's a candidate that maybe we'll pick a villa in Italy sometime and get down to Pompeii. I don't know.
Sounds like a great trip.
Yeah, spots to visit there as well. Yes, Professor Rousseau, you've got an interesting question. This is the Akbach to Greenland connection, Ally. How many eruptive events can be identified in terms of their severity in the ice core?
Yeah, that's a great question. Yeah, so there's definitely a limit to the ice core record, because I think the longest ice core in Antarctica, which was recently recovered, goes back 1 million years or so. But if we think about the Greenland ice core record, which has a very high resolution, annually dated record of volcanic events, we have the last 2,500 years at least down pretty well. And the severity of events is often associated with the amount of sulfur that's deposited directly on the ice sheet. So I showed for Okmok that there was a big sulfate signal that popped up around the same time as the eruption that also had ash in it. So it was very easy for us to say, okay, that sulfur came directly from the Okmok eruption. And the same has been done for many other eruptions of the past. I'll just quickly add that one complication with that is that volcanoes that are close by Greenland will sometimes deposit more sulfur just because of their proximity. So, for example, some of the eruptions in Iceland produced really big sulfur concentration peaks because they're nearby to Greenland, as opposed to, Okmok or even volcanoes in Indonesia, which had to transport their sulfur much further. So they can definitely give us at first glance an idea of the severity and magnitude of these eruptions, but oftentimes need more interpreting beyond just, purely the sulfur concentration.
David Simpson, you have an interesting point here. Well, can you go ahead and ask your question, David?
Sure, go ahead.
Oh, please go ahead, David. Yeah.
Yeah, I'm just interested in in earthquake studies, we've moved away from not moved away from the search, but are less optimistic about the search for short-term prediction and talk much more about long-term forecasting. And um, my question is that how easy is it for a major volcanic eruption to hide? I mean, we've had some cases of intraplate earthquakes that do sort of emerge without any. I think people would have been very surprised in 1811, 1812 with the New Madrid earthquakes in the central US. In Australia, there have been a number of very large earthquakes that were completely unexpected. Volcanoes, my sense is that it's more difficult for them to hide, but I'd be interested in your more professional view on that.
Yeah, I can take that. Yeah, like I said, volcanoes do give us signs. The duration of the signs may be hard to interpret or not up to our choice. There can be an example of Okmok from 2008 where there was unrest and it was detected, but it only took a few hours for the eruption to actually happen, and the ascent was really fast. In other places, we've seen Mount Spur active for months since April. When is the eruption itself? It's really hard to tell. The end of the eruption is also something that people really want to know and is quite hard to predict. There's an eruption in Alaska, Great Sitkin, that's been effusing lava for 3 years continuously. Why? It's hard to tell. But it's nice that it's not impacting anyone. But if there was a community nearby, they would have really liked to know, is this like that forever? So we're getting there, and the more data and the more types of data that we have are really going to help. And especially telemetering that data and doing it openly so that a variety of brains and skill sets can look at the data is going to be key to helping us do that.
For that. I'm going to interject a little bit. When Ewing came over from Lehigh, around 19 in the 40s, and co-founded Lamont in 1949, Joe Wurzel was a partner. That Joe came over from Lehigh as well. And I had the privilege of meeting Joe Wurzel, probably about 35 years ago. But we are visited today by Sandy Wurzel Brown, who makes a point about ash in ocean sediments. Some of you may recall that one of the things that Ewing and Wurzel and others did was sail on the Vima and collect mud samples everywhere. And apparently they found some ash. So Sandy, you want to go ahead and ask your question?
Okay. Has any study been made of the ash which was found in the core that Dad took on that Vima trip? And any idea how far the volcanic ash spread in the world or how major an eruption it was?
I guess this might be a question for Ally, actually, whether any of the ash that might appear in some of the cores, oceanic cores, might be helpful in what you do.
Yeah, I think it is absolutely helpful. So I'm not aware of the Wartell ash specifically, but I'll definitely look into it after this and get back to you, Sandy, because I am also very interested in the marine record of volcanic events, and that's because the marine record is actually much more reliable than the record on land. Obviously, we're lucky to be on land, but we're also exposed to lots of wind and rain and different erosive processes that being underwater you're a little safer from. So especially for older eruptions, the submarine record can give us a really good idea of, even directly what the climate impact might have been if we compare the nearby sediments. And then also is really important when we think about reconstructing the magnitude of events. So I think in one of my slides, I highlighted some drill cores that were collected around Santorini um, from some Lamont PIs. I think Bill Ryan maybe was on that cruise, but yeah, and that helps us get an idea of the submarine extent of many of these pyroclastic flows and different ash falls as well, because as we saw, the magnitude of these events is really important. And as many of these events happened at island arcs, a lot of that material goes into the submarine realm. So yeah, I think it's a really great question, and I'm excited to look into it some more.
One of the most spectacular phenomena of the last decade has been the Hunga Tonga eruption, Ally. I mean, what are some of the unique aspects of that one that make it particularly interesting?
Yeah, that's a great question. And I saw a question about underwater volcanoes in the chat. So I was excited to see that. Yeah, so the Hunga Tonga eruption was one of the largest, most explosive eruptions that we've observed in the last 100 years or so. It happened in January 2022, and it blasted a plume of steam and gas all the way into the mesosphere at 56 kilometers. So it was really a remarkable eruption to witness. And I think, I saw another question about how do volcanoes affect climate? And the interesting thing about the Hunga Tonga eruption is that it didn't release very much sulfur. Most of the sulfur that was erupted was actually, it went into the seawater around Hunga Tonga because it erupted into about 200 meters of water. And so there wasn't much sulfur that was injected to be able to have a climate effect. And that's why we're not all huddled inside right now writing our own Frankensteins. But the other interesting thing that it did was inject a lot of water into the stratosphere. And so that's something that atmospheric scientists are very excited about, seeing what effect that has and how long it stays in the stratosphere. Um, yeah, I could talk about submarine volcanism forever. So I'll end there and wait to see if people have further questions.
Well, let's keep talking about submarine volcanism. I mean, it's often said that the largest volcano in the world is, in fact, the mid-ocean ridge. And it's a linear volcano, so-called. In the marine work that Lamont does any of that transfer to terrestrial systems? Maybe not. Can you address that?
Oh yes, of course, of course. Volcanoes are volcanoes. It doesn't matter if there's some water on top, or ice or something. But in fact, the submarine environment allows us to study volcanoes in a way, in a more complete, comprehensive way, because a ship can just go over that volcano. And I'm thinking specifically about axial volcano or the East Pacific Rise, and shoot the seismic signal with an active source to image the subsurface. And that's something that would be almost impossible to do on land, but getting really highly detailed tomographic image and cross sections, seismic cross sections of the submarine volcanoes, highlighting a lot of information that is surely relevant to terrestrial volcanoes, like sizes of magma chambers, how magma chambers and magmatic systems relate to calderas, like an axial, caldera bounding faults. This is all information that is directly transferable. Also, detection of lava flows at the rifts, like was done with some of the acoustics data in the Pacific Rise, is again very, very relevant.
We have another interesting question from Demi Rousseau as well. What's next? Are we expecting anything big to happen, Ally?
I see that question, and it's one that comes up frequently, particularly because Yellowstone that I showed experienced its last super eruption 640,000 years, and Yellowstone seems to have erupted every 600 to 700,000 years. So there's this idea that we're sort of due for another eruption. And I guess I'll try and assuage your fears at least a little bit. One thing I think that's good is Yellowstone is very carefully monitored. So if we were worried about that volcano in particular having an eruption, we should know well in advance. And I think as far as the frequency of these events, it's very low, once every 10 to 100,000 years, maybe longer. And so it's not something that we worry about often. I think, the possibility that we have something of 1 or 2 magnitudes smaller is much, much more likely. And so that's sort of, more worthwhile to prepare for. But, maybe Einat from the monitoring perspective has insights on that as well.
Something can always happen. There's hundreds of volcanoes around the world. 80 are at some point of unrest. That something can always happen. Calbuco in Chile was an example. And what I'm really worried about is the ones that don't have signs or that are hard to predict. There's maybe, for example, phreatic or steam eruptions that happens in volcanoes. They might not be ginormous and throw gas and ash all the way to the stratosphere, but they're sometimes really devastating for anyone who's on a volcano. There was a big disaster in Japan about 10 years ago at Mount Aso, where steam just got too close to the magma and poof. So there's going to be problems when people are on volcanoes as tourists, as visitors, as people who live there. They're just in the line of danger, but there's a lot of benefits too. That's all said. So we always have to kind of weigh these together.
Let's follow up a little bit on that. AVERT is a really, if you will, it's a recent project, really, and it's really kind of unique in the way it's putting all things together. Are there organizations globally that are trying to do this or trying to leverage what AVERT is doing or otherwise are monitoring volcanoes? There's a question about Vesuvius, for example, in the chat.
Right. So every country that has volcanoes has a government agency that is responsible for monitoring. These are done locally by volcano observatories that are close to the site or centrally by kind of a volcano monitoring agency in the capital city or a city nearby. In Italy, that will be INGV. So they're doing a great job. They get a lot of practice monitoring Etna, volcano, and Stromboli, with keeping their eyes obviously on Vesuvio and Campi Flegrei next to it. So these agencies are mandated to do the monitoring and some science. And that collaboration with academia is really important for the academics to have the time and less of the responsibility sometimes to interface with the civil defense and the public, so that academics can maybe push the boundaries on the tools and the techniques and the ideas, and that collaboration has to happen, and it's happening, and it's really great. Following AVERT, there's a big discussion at NSF with NSF now by the community at the US to build something called SZ4D, or subduction zones in 4 dimensions, that is going to have a component of volcano arrays. So if potentially a major research infrastructure proposal gets funded, that would be able to fund 30 to 50 volcanoes in Chile and a little bit in the US as well, with these types of multi-sensor arrays following the AVERT footprint. So there's definitely that. There's also all sorts of communication channels like the World Organization of Volcano Observatories, or WOVO, that has databases there's global databases, there's the International Association for Volcanology and Earth Chemistry, or IEVSE. So these all have kind of ways for people to communicate and try to get together, because it has to be a interdisciplinary, interagency kind of work.
That's really, you didn't mention the Philippines. I remember during Pinatubo, Philippine volcano monitoring agency was very active as well. But you mentioned SC4D, and very briefly, could you tell us what that is?
That is a major initiative within the geoscience community, and it's looking at subduction zones, which, as you probably know, are the focal point for both earthquake activity, volcanic activity, as well as very active geomorphological changes. And trying to put these three communities together to study subduction zones and all these aspects of them over time. That's why it's in 4 dimensions. And it has been a research coordination network and a geohazards pilot effort. And now the community is coming together to propose a major research infrastructure on the tens of millions of dollars scale to really do an instrumentation at a subduction zone where we look at the volcanoes, where we look at the geomorphology, and look at the earthquakes.
Interesting question from Rosemary Hilbert, bringing to mind the cold weather currently having right now in New Jersey and New York as well. So, Rosemary, can you ask your question about Washington and New Jersey during the Revolutionary War? Well, I don't see it. Anyway, Washington crossing the Delaware. It was cold and wintry. Ally, do you know of any volcanic eruption that might have contributed to the bad weather?
Yeah, I love this question. So in 1779 to 1780, I'm not aware of any major volcanic eruption. However, Laki erupted in 1783 and did cause, we think, quite a big climate impact, particularly in France at the time. There was sort of existing political instability, and potentially the famine that was generated as the result of the Laki eruption could have contributed to the uprising and the French Revolution. So it's definitely a good place to look.
This is crazy. Frankenstein, the murder of Julius Caesar, getting tributes out of Egypt, and now the French Revolution, Ally. I mean, what can we expect next from the next eruption?
Yeah, I think one interesting thing to consider when we think about the catastrophic impacts of these really global events is that there's plenty of examples of civilizations that fare just fine through these eruptions. It's very easy to sort of pick out the places where civilizations are really struggling in the wake of famine and disease and whatnot. And I think what we see between those events and the commonalities is really that there's some existing vulnerabilities that are then exacerbated by these climate shocks. So I don't think we should be too worried, but I will say it's important to think about what systems that we have in the modern world that are susceptible to extreme cold or changes to the hydroclimate. And for Hunga Tonga, for example, one vulnerability that we sort of realized was in the eruption, a submarine telecommunications cable was cut, which severed some of the communications from the island itself. And I think that's one big hazard that we've been thinking a lot about since observing that for Hunga Tonga. Because the world that experiences one of these VEI 6 to 7 eruptions will be quite different from the Roman Republic, which experienced it 2,000 plus years ago.
Yeah, maybe we won't have tariffs if that happens. Anyway, I want to call out the grade 6 science class from PS 51 on Park Slope, Brooklyn. They've been listening in. They've attended some of these before, and it's a welcome participation by students. And I think volcanoes are always exciting ways to get people involved. Thank you. All right, we're going to close out now. Thanks once again, everybody, for attending and participating. Great questions, great discussion. We're going to hang on for about another half hour or so, depending for informal, unrecorded discussions, as it were. So those of you who wish to stay on, please do so, and we'll just have a casual conversation. We'll convene again in about a month, the second Wednesday of May. My gosh, May already. When we'll be talking about having another conversation with Lamont scientists. So thanks all. We'll end the formal program and hang on for informal conversation.